Hey everybody, it's me, Steve. It is March 12th, 2020. Time is 17:11 CDT. It's about 60 degrees Fahrenheit out, and it is Geo-Rant time, number 121. I am just going to address this briefly. I am presently working on another Geophiles episode, but I don't know when it's going to be up, so I thought I'd do this in the interim. I'm going to talk a little bit more today about geologic time, especially the Precambrian. As of right now, first of all, this is my source. This is available online, just this chapter. It's from this here, okay? From what you're going to see, I will show you some of my doings later that I had totally forgotten about until I was reading this and stumbled across this. There is a new one coming out this year, I believe, but it's not out yet, and I don't pre-order things, and it'll be the entire book. I'm going to get the entire book. But anyway, Precambrian. Here, I've shown this to you before. This is about the current geologic timescale. It's pretty close. We are going to deal with this part, okay? The Precambrian, as you can see, is kind of off on its own. It's not really something we use that much anymore. I guess it would be considered a super eon if you were to use that term. But as you can see, the entire time from the Cambrian diversification event to today, that's it to scale right there. And this is the Precambrian. The Precambrian is 88.1% of Earth's entire geologic history, plus or minus, 0.3% or whatever. The point is, it's a lot of it, all right? And quite frankly, what do you notice when you look at this time scale in the Precambrian, the numbers over here? What do you notice? I'll tell you what I notice. I notice very even divisions of these numbers, all right? Almost as if they are arbitrary. Guess what? They are. Because with the Precambrian, I've talked about this before, Geo-Rant 120. It'll be below if you want to look at it. The Precambrian wasn't really taken seriously into geologic divisions until about 2009 or so. And so we had a lot of these arbitrary divisions put in. As you can see, the Neoproterozoic here is almost as long as the entire Phanerozoic up here. We have huge amounts of time chunked out of the Precambrian. And we do have a lot better understanding of the Precambrian than we did even 10, 15 years ago. We are getting more solid dates. We are getting better geophysical data. We are getting better paleomagnetic data than we had before. So, a lot of people, including myself, and I apparently had forgotten I did this. This is my work, you'll see in a little bit, have tried to basically divide the Precambrian based on actual rocks, on the rock record, instead of these arbitrary divisions. And that is the way to go, because most time scales are divided off of, the rocks. That's how we do it. Now, there have been some, as early as 2004, some early Precambrian devised or suggested time scales based off of either fossils or the rocks. Now, I personally think we should be using the rocks, because the Precambrian, unlike the Phanerozoic, is pretty much on the macro scale. I mean, we have stromatolites, but those are colonies of single-celled animals. But on the macro scale, it's devoid of diverse life. It's hard to recognize the diversity of single-celled animals or life forms in general in the Precambrian. It's not a good way to divide it. Now, if there is some sort of biological event we can identify, and it can be found in the rock record globally, I think we can use it. However, I don't foresee that in the near future. What we need to be focused on more, I think, are actual geologic events. Like, most of you are aware of the impact at 66 million years ago, was it? 66, yeah. That wiped out a good chunk of the land and marine vertebrates. The old KT boundary, if you will. Well, there's an impact crater that it's been eroded through several orogenies since its impact 1.85 billion years ago. We have a firm date for that. Now, that likely caused a great, extinction level events globally, but it was with single-celled animals. But that marker right there, that impact, which was the same size or larger than that KPA impact, should be a division. And we have a firm date of it, 1850 plus or minus 1 million years. We can use that to divide time. Now, this is something apparently I was working on way back, well, not way back, about 5 years ago or so, that I stumbled upon. I did further divide these into periods, but I'm not going to show you that. Now, as you can see here, this is upside down. And other than upside down, this is the time scale, the accepted one at the time. And on the right here is my divisions. What you can see what I did here is I tried to align them with the arbitrary ones. I am taking that back. I don't care if it's aligned with the arbitrary designations. Maybe on the era scale, that might be necessary because of geologic maps and stuff like that. But when we start getting down into the periods, I don't think we need to worry about these numbers so much. And I'm not the only one who thinks that. In that, what I've already shown you here. Figure 16.34, somebody went and renamed all the accepted periods and gave more lithological equivalents, or gave more lithological boundaries, I guess you could say. It doesn't give the year on this, but it's because it was proposed here, so it'd be 2012. Now, this uses things like deposition of BIFs, which is fine, but it also uses glaciation's rise in atmospheric O2, and that calls it the oxygen, which is a good term, but we don't need to sit there and base it off of that. We can base it off actual stratigraphic packages like the Huronian supergroup. And the Huronian supergroup has 4 distinct unconformities, either on top or within it, and one below on the bottom that we can use to bracket geologic time, and I think we should use the Huronian supergroup. Now, the Huronian supergroup has global chronostratigraphic equivalents. I've gone over this before in my most recent geofiles. I'll link it below if I remember. But the thing about it is, wherever we put these divisions, other places in the world, you're going to get continuous deposition across a period boundary. I've talked about this before because unconformities don't continue forever, conformities don't continue forever. But that's a good thing. You want strata that cross these boundaries somewhere in the world in case you need to refine dates later. Because any proposal is going to obviously, if accepted, be refined later. But the Huronian has those good unconformities in it, and I've shown you before that we have good detrital zircons, good igneous dates of this stuff, where we can bracket a good period of geologic time. We can bracket it pretty well, all right, within a couple million years. So I think the Huronian, at least for the Paleoproterozoic, or the first part of it, should be used as the world standard. Like I said, it has chronostratigraphic units elsewhere in the world, but they aren't as complete, and they don't have the well-defined unconformities. And the good thing about the Huronian is the stratigraphy, even though it's passive margin sequence, once you get into the sediments, it doesn't really repeat itself, but at the base of each, above each unconformity at the base is a diamictite. And that's a good marker that is not present in other chronostratigraphic equivalents. So I think the Huronian would be a good way to divide the Paleoproterozoic. Now, as you can see here in this proposed time, they basically have the Rhodinian equal to the Mesoproterozoic. This isn't really a thing. If you're not really subdividing anything here, so you should just drop this. It's not necessary. It's a redundant. You're not dividing it. You're just giving it a second name. I don't know why they did that. But the Paleoproterozoic, I actually do agree with their markers here. But like at the end of it, they have it at 1780 MA, millions of years ago, and the reason why they put it there is the first appearance of sulfuric marine deposits. Now, and during their Columbian, it's the supercontinent formation of Columbia, Nunia, whatever, that's fine. That's just a period definition thing. But they had the first appearance of sulfuric marine deposits. I don't think that's a good marker, because that's where we think they are now. That could change, and that's the kind of thing that can end up changing by 50 million years. It's not the kind of thing that's going to change by 1 or 2. I think we have better markers for that, like the completion of the Pinocchian orogeny around the Great Lakes region in northern Wisconsin. That would be a good marker because we have good dates for that as well. That's not stuff that's likely to change by plus, that'd be pushed back 50, 60, 70 million years. So we should really stick with the rock record when we can, or a major event like an extinction level asteroid, meteor impact, comet impact, which Sudbury is suspected to be, something like that. But anyway, I guess I'm going to be getting into chronostratigraphy here again. I will briefly show you here. I did divide those periods and epochs and even gave them all names. And I hate to use North America as the gold standard for this, but especially the Midwest, but we have a lot of really good Precambrian events recorded here. And, not in Illinois and Indiana. Well, we might, but they're buried under Phanerozoic deposits. But in Wisconsin, the Upper Peninsula, in Ontario, places like that. And we have others out west in Montana and Washington and places like that, Idaho. Places like that were also good. And Arizona, as well. Wyoming. Stuff like that we can use as good markers because the Precambrian is pretty well preserved in North America. But anyway, this is going on 12 minutes. If you have any questions or comments, please leave them below, and I hope you learned something.